Okay. So thanks for the organizers for bringing me here. So I'll talk about extensions of GR with the MOND and ΛCDM limit, which retrospectively we named the Aether Scalar Tensor. Unfortunately, so I was planning to say something a little bit beyond that. Unfortunately, that's going to be very, very minimal. So let me just jump right through it, just to give you what it is, and then I will start discussing further. But basically, what is it? What is this? So it's an extension of GR. So you take GR and you add some additional fields. One of them is called the Aether field, which is a unit time like vector field, and a scalar field, in addition to the usual metric tensor of General Relativity. And so what it does, so it was constructed in order to, first of all, have a tensor-mode speed which is always equal to the speed of light in all situations, so they can pass the LIGO electromagnetic counterpart test, to reduce to MOND on the scales of galaxies when accelerations are of the correct order, reproduce gravitational lensing from baryons when every time you produce the dynamics, and lastly to give a good large-scale cosmology which is in harmony with large-scale observations of cosmic microwave background and dark structure, without having any, and all of this without having any dark matter, but having a cosmological constant. Okay. And it didn't just appear. It was based on a lot of previous work by many people. Some of them were here, and very notably the so-called Tevez theory from almost 20 years ago or so, building on work by Bob Sanders and Jacob Bekenstein. I will show came to be in disagreement with observations, but still the same ingredients are present in this instance. So as I will show, it reduces to MOND on galactic scales, ΛCDM, or cosmological scales. And these ingredients also, just to say, they have been introduced in different ways over the years, also in various different contexts like this. Aether field had nice history that you can find. So also, let me make also this comment, which you are not expecting, but I would like realized many times by talking to people that there is some confusion, and also even including today at breakfast. I want to emphasize this is not a relativistic MOND theory in the sense that it does not just depend on A0, and A0 does not control everything. So in particular, the large-scale cosmology is not to do with A0. So I wanted to make this distinction that it's an extension of GR which does have a MOND limit, because that was the whole purpose. But when you go to cosmology, the limit is different. Okay, so to me, a relativistic MOND would be something which really takes the inertia, the modified inertia. This is my opinion. It takes modified inertia and infuses it of Omicron and then infuses it with ideas from relativity theory. So just to make this point, in the same sense that GR is not relativistic Newtonian gravity, don't just take the Newtonian gravity and you put relativity in this sense. Right, so let me first start a little bit about Tevez because it's important to touch on how these things emerge from. So, Tevez emerged from the work of Sanders and Bekenstein more than 20 years ago, and has exactly the same ingredients. So there is the unit time-like vector field mu and a scalar, and this vector field is unit time-like with respect to some second metric, switching the notation from Bekenstein's case. But the metric that matter follows geodesics is constructed by combining these three fields in this particular form. So there are, in the initial instance of Tevez, it was conceived as a bimetric theory. So back in 2005, so the initial reaction from the cosmology community is that, okay, who cares? We know that CMB is there and this will not work. And they were very quick to dismiss it. But my take was, well, there is a full relativistic theory, just test it instead of arguing. And we did that in 2005, and we found that if you look at the matter power spectrum, you get this very nice looking red curve here, which passes through all the data. So this was not something which Tevez was meant to do. It was proposed having different things in mind, but still, the extra fields in the theory were such that it was able to fit the large-scale structure data. So that was a new ingredient. Just to show that this red curve is the case of GR plus variance only, no cosmological constant. At the same time, if you look at the CMB, it's almost there, but not quite so. So the last parts here are not so well fitted. At that time, the data were probably not so good, but with later data, this became apparent that this theory does not fit the CMB. There is one ingredient that is kept, which is that the quasistatic limit of Tevez is that of QMOND, which is that there is the usual, let's call it Poissonian or Newtonian potential, this phi tilde, which is sourced by matter in the usual way. And then there is a scalar, which is related to it using this formula. And so you can integrate these ones, get a curve, right? But in all situations, and this is already discussed in Bekenstein's paper, in all situations where the curve is subdominant, and this is usually the case because it decays faster than the gradients, then you can solve for phi and put it back, and you get the equal or MOND equation. Yeah. Now, QMOND has this nice feature in that you can keep this potential to be always Newtonian, and then by adding this scalar to get the field which gives you your dz, is phi. So accelerations are part of this. Then you can alter. You can get MOND basically trivially. It's like adding 1 over r squared plus 1 over r. Eventually, at the very, very large scales, 1 over r will win. So this is very nice. You don't need to do anything. You don't need any function for this. But what you do need to be careful is that you also have GR. And this is the issue already. It was already known already 20 years ago. So just to schematically show you what happens. So here is the MOND force here. You can add it to the 1 over r squared, no problem, goes right through, and eventually in the inner solar system, it's trivial that Newton will win. And the problem is this in here, which is the GR correction, which is very, very well measured already at Mercury. And so if you try, what you need to do, you can try to suppress this force coming from the scalar. You can do that by adding some higher powers of its kinetic term. But this is just not enough. So basically, you can take this p to infinity, you just get a constant force, which is already in conflict. It is not good. The way out of this is to add higher derivative terms. That's actually a paper sent by Moti here, where he extends QMOND by adding these terms. So this is perhaps a way to check further. But what I'm going to keep in for the rest of the talk is I'm going to keep having this free function, this j of phi, or the so-called interpolation function, which what it does, it basically turns the force from the scalar and turns it up to mimic exactly the Newtonian force. And when you do that, the effect is a renormalization of Newtonian gravitational strength. This is how it was also done in Tevez. Now, of course, I said that there was a new observation, which was gravitational waves since that time. And so the tensor mode speed has been measured to extreme accuracy. It's the order of 10 to the minus 15. So the difference, this alpha t parameter, which is the difference between ct squared minus 1, and this is the speed of light, it has to be less than 10 to the minus 15. So this brings Tevez in conflict with observation, both from the CMB and from the gravitational waves. And a few years ago, when this happened, the immediate reaction was that, well, this just rules out MOND. And I thought, well, Maybe it rules out Tevez. I wanted to check it again. But definitely, I mean, it's preposterous to say that this rules out further. I think that this was based on the biometric structure of Tevez theory, and so it was the argument was well, you have one metric for baryons and photons, and then you definitely have to have the second metric to get the MOND theory, and those two, the tensor modes will have different speeds, and therefore this whole thing just doesn't work. But you have to be aware that the metric is not unobservable. So in order to do this properly, you have to do propagation of the tensor mode. So here is the Tevez Lagrangian in the more generalized form. These C1, 2, 3, and 4 are constants, which are there because of the Einstein ether theory. What this one is just the first part here. This is the action for the vector field, which was put in order to give you length. You work out the tensor mode, and this is what you get. Okay, this equation here, so which is a wave equation for the tensor mode. But you can see that the constants feature here, but also very interestingly, there is a function of the scalar. This is the background cosmological scalar, which features in front of the gradient. Yeah. And so you can just take the ratio, find what is the tensor mode speed. This is what you get, and so there is no way you can have this to be equal to 1 for any type of cosmological evolution. For phi, it has to be very, very contrived and choose a constants and the initial conditions together so that it's okay. But then, suppose you start from the same equation and you say, well, what if the CIs depend on the scalar? Yeah. If you do that properly, you have to include also this term here with the derivatives. And so you just choose this term here, C1 plus C3, to be exactly this function. And when you do that, you get back a tensor mode equation, which is exactly like general relativity. And this has nothing to do with the MOND limit. This is just cosmological. So you can do this exercise without touching MOND. Okay, so this is great. So this is what basically led us to think, well, if we can do this, then how about trying to go back and see whether we can also get good cosmology of it. And the starting point is transformation by Zlotnik, Ferrer, and Starkman in 2006, where they just took Tevez and recasted the whole thing using only one metric. By just solving for the constraint, you get two fields now. You have this B field, which is a combination of these three and the metric. And now this B field is still time-like, but it's no longer unique. So it has exactly the same number of degrees of freedom. And if you take their action, I'm not writing it here, but you generalize it to make it as general as possible. These are all the possible terms that you can have up to, which don't have higher derivatives. And these DI coefficients are actually functions of B squared, which is this, and some, let's call them non-dynamical fields, mu and u, following the prescription of Bekenstein when Tevez was built. And so you have a function of mu and u here, which will eventually give you the MOND behavior. Okay, so you have 9 functions. There are these DIs here, which is u, and there is the 8 DIs. So what do you do next? Well, and first, just to say that there is one term missing here, this the D3 term. The D3 term is what would give violations of the CT plus 1 condition. So this action already has gravitational wave tensor mode speed equals the speed of light already from the start. Okay, so then we thought, okay, we need to give cosmology. That means there will be some time dependence on these new fields. But the question is, what should that be? Okay, there would be. So cosmologically, they would give some energy density, but okay, there is a big choice. And so there we appeal to the observations, which since 20 years ago, things have drastically changed. With the excellent Planck data, we now have tracked like 7+ peaks of the CMB. And so we know that there should be something which looks like a dust component in the universe, and this is unavoidable. If that component has some equation of state, that equation state during recombination has to look pretty much like dust. If you track its energy density, and this is just from data, these observations tell you that at the time between equality and recombination, it pretty much looks like it's going as 1 over a cube. So this is the normalized density where I'm dividing out by a cube, 1 over a cube. Okay, so can do the same thing perturbatively, so the speed of sound of this component has to be also very, very small on very large scales. And so what we thought, okay, can we take that general action and construct such a, use the field content, so the vector field and the scalar, to construct something which cosmologically looks like you have this extra dust component, but at the same time it is the same components which give you the MOND behavior. So you don't have to add extra ingredients. And there was a model already from a long time ago where this is done in the context of VR. Basically, you take a scalar field, x is a kinetic term, and just displace it away from 0. So you introduce a minimum. So x, the kinetic term goes to 0, not when x equals 0, but when x is some constant x naught, which cannot be 0. And when you do that, you get energy density which scales as 1 over a cube plus corrections. So since we have this model, we try to incorporate this into the Lagrangian. And so what you do, you have to choose these DI constants, and this is the choice which leads to this. Quasi-static limit is Q naught, universal G Newton, universal A naught, they don't depend on any fields. Constant Planck mass, minimal coupling between metric and the scalar, shift symmetric action, get these Schroeder solutions, and also some additional simplifications which we just chose for simplification reasons. And the endpoint is this action. So now you have the rich scalar, the B field, so you get this 1 over B squared and so on terms, so B cannot be 0, but it's time-like. And this is the only terms which survive. And this mu and nu are the non-dynamical fields which are there to give you MOND and cosmology. So this action has a global scale symmetry, B goes to lambda B. But what you can do is you can find an equivalent action by recasting this B field in terms of the scalar and the unit time, like going back to the initial way of doing this with Anders and Bekenstein. And so this is the result by including a Lagrange multiplier. And in this form, these are exactly equivalent. The scale symmetry becomes a shift symmetry. Okay, so this is the ingredients for Aether Scalar Tensor. It's called Aether Scalar Tensor because of the Aether field and the scalar and the tensor. So very briefly, how much time do I have? A lot of 7 minutes. Sorry? 27. So first of all, it gives you tensor more speed equals 1 always. This constant is in the same fashion as Bekenstein had it there, in front of the kinetic term of the vector. This term here is actually very important, and it comes out, it is what exactly leads to the Q-MOND behavior. So you cannot set this to 0. And it has to come exactly with this precise combination. And that's a Lagrange constraint, and so everything happens here. And given that we have a unitary-like vector field, it means we have a dynamical preferred frame. And so we can choose to split derivatives of the scalar perpendicular and parallel to this preferred frame. And so we construct these two variables. A y variable, which is the spatial, takes care of spatial gradients, and so in spatial quasi-static situations, this becomes just gradient y squared. In time-dependent situations, when it's relevant is this q variable, which it has to do with time evolution. Okay. So something which has come up a lot in questions as well is, well, isn't this some kind of dark matter? My answer is no, and there are reasons for that. The first one is the following. These fields have backgrounds. And so the vector field, so just as a metric has a background you usually expand on, in this case Minkowski, so do the other two. So the vector field, the angle component can never be zero. It always has to have a background because it's unit time-like. If you expand on Minkowski, then that's just -1, and then you add some perturbation, but the perturbation is again not free in the angle component. It's completely fixed in terms of the metric to linear order. This spatial part is free. It's fine. And the same for the scalar, because it has to have this behavior which I'll discuss further in a moment. Phi dot cannot be zero. It has to be a constant, and that's to get the cosmological. The spatial part can be. Okay, so once you have this, then inevitably these components have to mix together on any background. So there is no way that you can actually say, take these things apart and say these are good degrees of freedom, I call this the dark fields. Because by doing transformations, you can always mix them with the metric, so you can never distinguish what is what in this sense. This is something which exists in other theories which were not related. We didn't have the MOND limit. So, for instance, this behavior with the scalar is part of the so-called closed condensate model, and the same behavior with the vector is the so-called gauge closed condensate. So, in this case, both of these are part of the theory. Okay. This is the second order action on Minkowski. The first part here is GR, and then you get these additional terms. All of these terms here are gauge invariant if you do these gauge transformations. So this A dot, that's grad function of node, that's gauge invariant term. This term here is also gauge invariant, and so is this. And so here is the other parameters which enter. Q dot is what will feature in cosmology. Lambda is I already introduced this as so-called screening parameter. I'll discuss it in a while again. But let me emphasize that apart from the diffeomorphisms, once you go to the linearized level, and then you impose, you impose a static, that you want to give into quasi-static configurations, then it's an additional emergent symmetry. So this is not a diffeomorphism. So it's just you have the freedom to exchange alpha with this scalar by doing transformations. So I will discuss it again in a while. One can analyze the normal modes. So there are the fact that you break essentially time diffeomorphism introduces some massive modes, and so the vector has two massive modes with a mass given by this particular combination of parameters. And the scalar mode also gets the same mass, but also gets the speed of sound, so it does not propagate with the speed of sound. And then you have to impose constraints to make sure that these relations are healthy. And so that says that this constant K2 has to be positive here, and this KB has to be between 0 and 2. And the lambda as a string parameter has to be always positive. And once you have that, it means that at the linear level, that things look healthy. And on top of this, what you find is some additional mode where omega is just 0. It's a non-propagating mode. If you think about it, it has a linear time. It acquires a linear time dependence. So it's not an oscillator propagating. What you do then, you find the Hamiltonian for all of this. Hamiltonian for these modes is always positive, but the Hamiltonian for this mode has some interesting behavior. It is positive for all scales, or all, let's say, at large momenta, so all k numbers which are bigger than this mu parameter here, which I'll show in a while what it is. But when it's smaller, then it's negative. And this is actually a linear G stability. It's G stability because it depends on this K number here. It's always present, and it's also present in some other theory I will discuss at the very, very end. And it is also present in the case of the gauge condensate. So it's the fact that cosmologically you have to have a kinetic term which is shifted away from zero in order to break the time inflow buffer. Okay, so now let's look at the quasi-static limit. Again, let me emphasize the symmetry here, which is present in the case of quasi-static fields. So what you do is you take the vector field and you shift it by a gradient of something. This something here, this C, has to be time dependent to make sure that things stay quasi-static. You do the same to the scalar. And so if you take a combination of the vector plus the gradient of the scalar, you can make sure that this C here cancels, and also this is an additional symmetry. Also, in the same fashion as the Q-MOND, let me ignore the curl for the vector field because you only get, anyway, you get MOND only when the curl is zero. And when the curl is very large, then you will not get back the MOND equation, you get something else. And so I can use the symmetry to get rid of the vector field completely, in the sense that I am absorbing it into the scalar. And this is just for simplification reason. Right, so when you do that, this is what you get. This y parameter is just gradient phi square. Q becomes just a constant, you know. And so this function f just turns into a function of y only. At the same time, you get a constraint in the action that the two potentials have to be equal. And what this does is it ensures that for any source configuration which gives you MOND, and so all the dynamics are fully captured, that source will also give you the right gravitational density. So that's fine. But then, when you find the field equations, there is something in addition to the standard MOND. You get this additional term here. And this is because of this Q term not being zero, the Q naught. And so if mu equals zero, if you look at small enough scales, you get back the Q-MOND equations. It all follows nicely. But when you get to scales which are very large, away from sources, then this mu term actually does play a role. And you will have to start, you will start to see departures from MOND in that case. Very briefly, I don't want to spend time on here, but I think this is known to many people in the audience. So you need to have this function to have two specific limits. Has to be proportional to the graph phi square in the Newtonian limit to get the scalar to exactly track the Newtonian potential. So lambda is what I call the screening parameter. If you take it to infinity, then you have to add higher derivatives to screen it. And then in the MOND limit, then you need to have, to get MOND, you need to have this particular combination. So you have a grad phi cube term in the action. Okay. It is what it is. And then you can build the function you want. This is one particular example, but not the only one. But one thing which emerges is that this function has to be non-analytic, because you can see that these two limits is exactly the opposite of what you would expect, in the sense that you want a higher power term to dominate when the gradients are smaller than A0, and the opposite. So you can do that, but the function just cannot be some analytic expansion of this term. And the other issue is that because of the cubic power here, we are forced to take absolute values. And so you cannot really expand this in Fourier space in the normal sense. That's something to say. Okay, so this is how it looks like numerically. So here, what I'm showing is spherical symmetric points or solutions, or at least outside some extended source, but this is all in vacuum. and then you see how everything happens. So Newton turns to MOND, and then this additional new regime because of this mass term here. This mass term is what comes about because of the breaking of the time before moments. It goes together. So that's also needed for cosmology, which means that you cannot really send this to zero. You can make the inverse mu to be very large, so that you can send the scale to be very large. You can approach the horizon, that's fine, but it cannot be zero. The mu cannot be zero. And it's a mass scale which is less than 10 to the minus 11. The break here is a usual MOND scale, in the standard way, curves with GM over A naught. And then where these oscillations dominate are exactly here. So there is a new scale emerging, which is this particular combination of constants plus some modifications due to initial conditions. Actually, I'm not mentioning here, but this is published in an article a couple of months ago. It's on the archive with Seligman and Peter Verheyen. So there is much more, in that article you can see much more phenomenology of what goes on in different situations, how things depend on the constants and so on, and also on the boundary conditions. So, but I'm not sure here is the dependence of this scale on the boundary conditions. But this is actually the maximum you can get out of it. So you cannot push the scale further than this number, and it is this particular combination of constants. There is still more work which is happening here. So Ameltis here is also working on this and looking into the cases where you actually have extended sources and isothermal profiles. That's something which will come up hopefully soon and have more relevance with clusters. Okay. Now another point I wanted to make, again, going back to this issue that people sometimes discuss, is why don't you call it that matter, is the following. Looking at these quasi-static field configurations, remember that this is just baryons. It's just a baryonic density here. But if you set the baryonic density to 0, then nothing survives. So the only trivial solution is that the gradients are all 0. In other words, it's a very distinct difference from the case where you can, in lambda zero, when you have dark matter clumps, this is very different. If you don't have any baryonic clumps, there should be nothing left in this case. Okay, so I think this is quite important. Now let's go to cosmology. So that's a case where the scalar is time dependent, the vector field is completely fixed. So I'm just setting the A naught, I'm choosing coordinate system, A naught is just equal to 1 in this case. And so there are no special gradients, y is equal to 0, and q is just a function of t. You plug it into the free function, you get a function k of q. And this is something which has been studied widely in cosmology in the context of inflation and dark energy under the name of KSS. And here is where the Scherer and also the post-condensate models come into play. So you need to have this k of q to have a minimum at this q naught value. So here because we had the vector field to play with, we kind of broke away from the having k of depending on the full kinetic term of the scalar. Rather, it's enough to have it to depend on the term which it's the contraction of the vector field with the scalar, so plus 1q. This q naught cannot be 0. It is a parameter. It has to be there, and you can fill it with data. So it's not something that you choose in any particular way, and so is this k2. And it is the same term, this q naught, it is the same term which introduces this new term that I showed earlier, this master. They go hand in hand. You cannot have one. So how does this work? Well, these are the equations of motion. because of the shift symmetry, there is a conserved current, so you can solve it. That turns into this initial condition. So you can avoid this. So if you want, this dust density cosmologically is given by an initial condition in exactly the same as lambda CDM. So it's not something which depends on the baryonic density. So I need to make this point. And so you get corrections. So rho goes as 1 over a cube plus corrections, which K becomes stronger in the early universe. The equation of state also scales with time. Speed of sound also scales with time. And then you get corrections which go as 1 over to the 6 and so on. This is what has been called, this particular thing is what has been called the Higgs space for gravity in the ghost condensate literature. And it's universal in the late universe, but in the early universe, it all depends what is your choice of K. So you can have whatever behavior you want in a way, or required by observations, but the late universe case is universal. Right, so this is how W looks like for different cases of K. So here is the big molecular synthesis down here, equality is here, recombination is right here. One point I want to make is that because mu is related to Q naught, and because we need to have this, the whole point is to get MOND out of this, you need to have this scale to be very, very large. It's just some conservative estimate, it can be probably even larger, depending on what observations tell you. But at the same time, when you calculate what this W naught, which gives this, it gives a 0 point here, how early this shift happens. When you calculate that, you find that it's inversely proportional to mu squared, weighted by h naught squared. And so these two things are exactly related. And you want to make sure that this component has a very small equation of state already after, well, it has to happen before equality. It cannot happen afterwards because then the CMP is messed up. And so that is a constraint that this W naught has to be, well, sorry. This translates into W naught being bigger than 10 to the minus 8. It's here. So if you extrapolate this back, you will have order 1 W already at the combination. This is bad. Because the data tell you otherwise. And so you're already at the point where you can already start ruling out the simple models, these things like phases. And so the way out of this is to use some K of Q, which has some other form. There's nothing unique here, you can play with this. But it's such that you can suppress the equation of state throughout most of the history of the universe. So you can have W to be really, really small, or 10 to the minus 8 or smaller already earlier. So when you do that, then everything is phenomenal. Okay, so to look at the structural formation in CMB, you need to check perturbations. So here is the metric in the conformal Newtonian gauge. Again, you have the two metric potentials, scale factor, and then you do the same for the other fields. So the scalar is expanded on this background, plus a small perturbation. The vector field acquires a scalar mode. I'm interested on the scalar modes, which are relevant for the CMB. And then what you find some wave equations for these fields, which I'm not going to show here, but you can, because these are linear equations, you can take linear combinations of these. So you can combine things together into these new variables, E, chi, and gamma, and then a further linear combination into something which looks like a density contrast for some new component, a velocity divergence, and then a pressure contrast. And once you do that, then you get equations which look exactly like an additional fluid in the case of VR. But then the pressure is not it's not free, but it is given in terms of the evolution of the remaining fields, in terms of alpha and E. So Depending on what is your function here and how phi behaves, then you can have also difference of behavior. But if you take the limit that w goes to 0, equation of state, and the speed of sound, which is what I was showing earlier, then you find that the first set of equations will be exactly like in the case of a dust component, like CDM. And then the second set of equations effectively decouple in the sense that these equations here do no longer depend on the second set. So these set of equations are still sourced by the first one. So they do their own thing, but they don't affect what goes on here. So the same behavior which gives you a good background cosmology then also leads into perturbations, as you would expect in the case of lambda CDM. And this is a result. And here I'm showing the CMB temperature and polarization spectra, as well as the matter power spectra. Actually, the periodic table really wanted us to push it as close as possible to Planck, just to see that it really does fit, and this is the result. These are the residuals. This is not an MCMC fit. It's just playing by hand with all the parameters which we have at hand, just to show that you can fit the CMB very nicely with this thing. Right. What are the parameters? There is just to summarize, the KB is a constant, Q naught and K2, plus the initial condition, which gives you the background cosmological density of this dust. Okay. And so to summarize, this is an extension of GR, introducing new fields which transform into each other using a diffeomorphism of the background. Using a diffeomorphism, because you always have a background for these fields. The same fields which give you MOND is the ones which give you good cosmology and lensing, and make sure that the speed of tensor mode is always equal to the speed of light. It is, just to emphasize, it's not a MOND theory in the sense that you don't just take the MOND and you fit cosmology with it, but it is an extension of GR which has the MOND and lambda CDM limits appropriately. And it is not an addition, it's not a new theory of dark matter, but rather it is a genuine modification, genuine extension of GR because of the transformations of the fields with each other. You do expect to get some non-zero ppm parameters. I think that's unavoidable. That's something to be done. Also, something that I already mentioned is that if you, in quasistatic cases, if there are no baryons, then everything vanishes. So there's no dark matter collapse, if you like. Because of these new fields, you expect to get additional gravitational wave polarizations, in particular scalar gravitational wave radiation. I don't know what that is going to be, so that's something to be calculated. But it would be interesting to find out what it would be, what would be expected. So this is the beyond part, which unfortunately we have not put on the archive yet, but I wanted to pre-advertise here. So in collaboration with Luke, who is coming, I think tomorrow, we found that actually you can even remove the vector. You can get even simpler version of this, where only the scalar is present, and all the features are kept. So you still have the MOND limit, you still have lambda CDM. So that's something hopefully will come out in the next, I don't know, maybe at the end of before the end of the month. But we'll see. Plus some additional features actually, which are quite interesting. Oops. Right, so just the road ahead. Okay, 2 minutes. Okay, there's plenty of time. Just to. So what is the road ahead? There is some work which still needs to come up. So One is the ppm parameters already mentioned. That's important to calculate. Black hole solutions I didn't discuss, but we already have some very interesting solutions based on this with my student. Spherical is, well, there was already a spherical symmetric solutions paper, which it's already on the archive, and there is a follow-up by Amel here, looking also into extended sources and isothermal profiles. Hamiltonian formulation of the full nonlinear theory that's actually finished. This draft is going through some fine-tuning at the moment. MCMC, of course, to find out what are the bounds on all these parameters. That's important. But just wanted to mention a few things again. Is again my view. There is this MOND term here, which is non-local in Fourier space. You cannot expand this in Fourier space. For me, this is something which has to be refined. It's the same term which existed already for almost 40 years, going back to 1984. Perhaps there are better ways of doing this, I don't know, but I think it might be nicer to have something that you can actually easily expand in Fourier space, from the field theory perspective. And also some ways to somehow find a function which is expandable as a series, no longer, it's not a linear behavior. Perhaps there are ways to do that. Choosing new fields, so using this extended Q-MOND, or other ways of doing this is still open. Right, so I'll finish here, and I'll take questions.
So I actually have a short and maybe a shortish one. So how can you ever hope to get rid of this power of 3? After all, MOND has to be nonlinear, so Fourier means a linear theory, so how can you sort of...
Yeah, by that I mean when you have, let's say that was part 4. Suppose it was part 4, then you don't have to take square roots and everything, and so you can expand things in Fourier space to higher order. You have mode coupling and so on, but at least it's under control. In this case, you have to take a square root outside integrals, and it's just strange.
The other thing maybe about possible affinity of with MOND even in the cosmological context. So if I'm not mistaken, you have like 3 parameters, Q naught,
right,
and 2K parameters, KB and
right.
If I'm not mistaken, Q naught has
and the initial condition, yes.
Q naught has dimensions of acceleration. It's phi dot.
Q naught, yeah, it's well in this, yes, it's inverse length, yeah.
It's fine, yeah, but actually in my language it's acceleration.
Yeah.
And the K's are dimensionless, aren't they?
The K2 is dimensionless, and
KB is also.
KB as well, yes.
Yes. So, and you still have some freedom in choosing the potential for phi dot. You mentioned Higgs.
Indeed, yes, yeah.
Isn't there a possibility that Q naught would actually be roughly A naught or the order of A naught?
Good question.
And then I think I checked it, and it is possible.
It might be. I'm not excluding it.
In which case, you're not at least adding another acceleration constant.
No, sure, yeah.
So it would be nice if you could find such a.
Yes, at this point I just let it free and check what data say, but it might be, as you say, I mean, it would be interesting to check that at least a subset of the allowed parameter space has exactly this. I don't know, but.
So I have a couple of quick questions regarding the CMP fit. I guess you at least know what the best fitting parameters are. So with regards to, so you didn't write down what the cosmological parameters are, but what's the inference on the, what's the best fitting Hubble constant? Is that higher than what the Planck team got?
So we didn't do a proper LCMC fit, so I don't have any distribution for this.
No.
And so I don't even know what the best fit parameters are because we haven't done this. I know what are parameters which fit well, in the sense that I showed you. All the cosmological parameters, so the other cosmological parameters are not identical to the best fit from Planck.
Yeah, that's
not
what I would
possible,
expect.
right? But they are within a few percent. So within.
But the Hubble tension is only a 9% change.
So if you are thinking whether this could solve the Hubble tension, perhaps in principle, but I would think it's unlikely for some other reasons.
Okay,
because of some other constraints of some of these parameters.
Okay, so that's you'll have to look into the MCMC chain.
Yes, I mean it's better to do
but
that.
It seems unlikely at this stage that it would change the cosmological parameters at very fast.
It's possible. Well, if you let everything free,
yeah,
I'm sure you will find some better fits with higher Hubble parameter. But there are other priors on some of these parameters coming from elsewhere, like PPN and so on, which could change things again.
All right, fair enough. The other thing I just want to ask quickly is that in your model, because the effective density of the dark matter that comes in on the cosmological scale, so regarding this Q0 or the I0 parameter, I guess in principle that is that cannot be set to 0 in this model as well, in theory, right?
Sorry, so again, you want to set Q0 to 0?
Yes, in principle, because you have a pressureless dust component, something which mimics that, right?
No, Q0 cannot be 0. If Q0 is 0 exactly, you don't get dust, you get radiation at best, or kination, something else. You cannot get dust solutions.
No, exactly. So in principle, it's possible to do without that component. There wouldn't be a pressureless dust component at all.
Not exactly, there wouldn't be pressureless dust, so you wouldn't be able to fit cosmology.
Well, unless you put some other pressureless dust component in.
Yeah, but then you're putting in dark matter.
Yes. So in principle, with your equations, that's still like a possible way to do it. That you put in dark matter and you.
Well, you can always put dark matter. We already know this, so.
No, but even with your equations, which have a MOND limited galaxies, you could still put dark matter in for the cosmological context.
It has to be something which doesn't cluster on
galaxy scales.
Galaxies.
But that would be consistent with your equations to do that.
Yeah. Okay. I mean, you don't even need this at all. You can already do this for Tethers.
But Tethers has additional problems with the
gravitation. You can just have some, exactly, you don't even need to have this scale.
But Tethers has additional problems with the gravitational wave speed, whereas your model solves that problem.
Sure, fine.
Okay, thank you.
Yes, actually, other people have been, it's okay? Other people have been dancing around this question, I think. What is A0? Where does A0 come from?
That's not part of this at all. So we just took the model and we constructed this. But we don't answer this question.
It is an interesting question. That
it is, yeah.
Okay.
Of course.
Yeah, so I'm wondering about your argument that the scalar field thing is not dark matter.
Right.
To lay on my cards on the table, I think it is, but so I wonder about this. So, for example, you showed the quasistatic limit equations, and you said something like, if you set the baryon density to 0, you get 0 field, gravitational field, or something like that.
Yeah.
But doesn't that depend on you choosing this very specific boundary condition for the field phi, which is equivalent in the dark matter picture to choosing 0 dark matter, which you can't do in general because that comes from cosmology or something like that.
So you have to then think about it in terms of cosmological simulations. But if you just keep on a quasi-static relaxed system, At least in spherical symmetry, there is no other way to get that. You
Yeah, but
can
how-
maybe find some, but even then, I mean, you need to have some support around some black holes or something, which will give you something else.
But you have to choose zero boundary condition to get zero field, even without any baryonic matter.
Zero boundary.
So the field phi appears without derivatives in this equation, the gravitational field. So its absolute value is physical, no?
So say that again.
Or maybe we can just look at the equations. Yeah, that one, that top left, right. So in the second line, the mu squared term is multiplied by phi.
Here.
So, right, and you have to choose what integration constant you add to that, or what boundary
Yes,
case you
so
choose.
actually, in contrast with pure MOND, essentially the boundary condition of this field here is important, and you can change the solution. But that's the let's say you said that you have some source, you said it because of the source.
But even if you have no source, no baryon density, zero set baryon density, you only get zero gravitational field for very special boundary condition. No?
I don't see how that. I think the trivial thing is that you get back to the trivial thing and everything is zero. I don't see how that. You have to have something which maybe there is some black hole there in the center that generates something, but otherwise.
It's a degree of freedom, so why do you set it to zero?
Well, you don't. What do you set to zero?
Well, maybe we should discuss later. I think I'm taking enough time.
Okay.
We know that in electromagnetics you can remove 1 degree of freedom, say, by taking a Coulomb gauge.
Right.
If I understood you correctly, you said that the A vector potential can be removed, right?
A vector potential. Well, no, it's the. You mean in this case?
You announced the paper and the last slide.
Well, you ignore the. Well, it's to get MOND out of Q-MOND, you say that the curl of the vector potential is zero. So the curl is. Is that what you mean?
Okay, so if the curl is zero, then the vector potential is a gradient of a function. This is what you
Yes.
say.
Yeah, exactly. So only the gradient remains. Yes. Yeah.
Okay. So my question is, can you do better? Can you remove this scalar altogether?
Well, there's a symmetry, so you can. Where is it? Here. You can choose the gradient of the vector to be zero and keep everything in the scalar, or you can choose the scalar to be zero and keep the gradient of the vector, or both.
Okay.
Yeah.
Thank you.
But you cannot remove both.
I see.
So thank you. I mean, first I want to remind everybody what a great accomplishment it is to be able to fit the power spectrum. Right? For forever we've been told the only way to do that is rigorous ΛCDM, when in fact there's this more general dust-like entity. But my question is, you know, you show the fit at Z1000 and at Z0. Does that mean the growth is rigorously lambda CDM-like? That is, if we could measure this at Z1 or Z5, would it be different? Or
Right,
exactly
on linear scales it is. But what I didn't discuss here at all, because it's not so trivial, it so happens once you bring in nonlinearity. So the question is, how do you find what is the quasi-static limit? And so once you go to nonlinear scales, you might have different growth behavior. I don't expect that it will be exactly the same, and that would be interesting to check. Just to mention that how to get to the quasi-static limit is not as trivial as in lambda CDM in this case, because in lambda CDM, you take the linear equations, take the quasi-static limit, and you recover Newton. Here, you don't want to be recovering Newton, you want to recover MOND, which is a higher order curve. So you don't see this, if you do this on linear theory, you get nonsense.
Hi, Skordis. Very nice presentation. Lots of questions still left. But I will ask one. Can you admit one important drawback or observation challenge for the model?
Drawback. What do you mean by drawback?
I mean, which things you think is hard to fit with it on somewhat of a large scale?
I don't know about what you mean by hard. I mean, there's certainly many things.
Simulation, for example, embody simulation.
There
Do you
is
think
many things one has to check.
do you have some confidence it will go well, or? That's what I mean.
I mean, there is plenty of systems you check. You should check PPM parameters for sure. You know, if clusters. Okay, it will be different amount because there are more things happening. I mean,
Yeah. Okay.
everything, right? I mean,
Okay.
it's
But not obvious anything is difficult. Not obvious at this stage.
I mean, on large scale, you need embodied simulations which take into account this field. So no one has done it yet.
Okay. Okay. That's perhaps the one. So on the I was just want to continue what the previous person was asking. So is it through the may I call it the gauge transformation? Can you make the metric to be always Minkowski just by choosing a gauge?
No.
Oh, okay. So we don't. Okay. No, we don't have.
What do you mean? I mean, you will not have any potentials. Or
Yeah, if you go to your H
you mean here?
mu. No, the one I guess the earlier one where you showed the H mu how the three things related. H mu.
No, there are stuff here that you can
Yes.
not remove using vectors and scalars. You cannot remove gravitational waves.
For sure.
And there is more degrees of freedom.
Yeah, for sure. Okay, just yeah, you only have 5 free functions. 4 free functions. Yeah, the chi's. Yeah, okay.
I just have a question on the MOND correspondence and the, you had a slide with the cosmology and showing the constraints and how the MOND correspondence somehow ties on to the Friedman-Robertson-Walker scheme.
Right.
I just want to understand, is there a prediction for redshift evolution of the Tully Fishers, let's say?
Of the Tully Fisher.
Yes, I mean the amplitude of the Tully Fisher or the flat rotation.
Well, in this model, A naught is a universal constant. If you embed this in a cosmology and you have a scale factor, depending on which coordinate system you choose, I mean, so you will have the physical gradients will have a scale factor in them, but that's because of that's the usual things. Nothing.
But there's no redshift dependence of A naught, let's say.
A naught itself, not. But when you look at if you want to look at the MOND limits and treat the scale factor as some time-dependent function which is slowly varying compared to what you're checking, it will still be there and it will feature.
So there will be a redshift evolution of the Tully Fisher relation.
You want to think of maybe. But this is the same as intelligence. It's not a new feature of this.
Hi Kostas, thank you for the very beautiful work. This is really impressive. So I have a question about the very early universe. So you made a point that you can choose the free function in Q to essentially get all the classic results about BBN and so on. So I was wondering whether you can actually alter a little bit the functions that you choose to change the timing of BBN. In particular, I'm thinking about the lithium problem, whether one can, rather than converging exactly to standard cosmology, try to solve that problem too, or alternatively, whether you can fit the CMB with a slightly different value of omega bar that would go in the right direction to get the right lithium abundance?
Probably yes. I mean, you can choose this K to be radiation in the universe, so you can have an extra radiation component, or almost radiation. You can have that would change PV and LU.
Thank you so much. Although most of it is a bit dense to understand, I wanted to understand this in terms of cosmological simulations. So, on the larger scales, this should get the structure formation right, and on smaller scales, the baryons should collapse into galaxies without any dark matter halos. Have you tried like this model in like a cosmological box or something like that, or is it just like in the initial stages of it?
Yeah, this is all at the moment. So we haven't done any simulations.
But ideally, that's what you expect, right? On large scales, like all the collapse should happen without dark matter halos around it.
Yes, eventually. When you settle to quasi-static situations, so when it's something in between, then the time dependence of these fields will play a role in a way which is different than that scale. So this is, I think, related to stasis question.
Yes,
different growth as well. But I don't know what the answer is. I don't even know if it's actually going to work.
Looking forward to it.
Thank you very much. It was very impressive. So I have a question. When you were showing the oscillatory phases, I think that in the scale of the local group, it basically corresponds to the outer part of the local group. And I have two questions for that. So do I understand well if I can analyze this as in the lambda stem framework as clump of dark matter that will be completely isolated really outside when you are in the oscillatory phases? And so will it be detected with weak lengthening of strong lengthenings, for example, to get completely independent clump of pocket of potential width? And also, will it be possible to get resonance effects at this scale?
So you're talking about these things here?
Yeah, exactly. Yeah.
Yeah, I mean, this is an idealized case of a point, let's say, in vacuum. Once you add matter in there, things change. So you can even erase the oscillations. It's just the behavior is going to be something which is not Mondian when you get up here, but it doesn't have to have oscillations necessarily. This is special.
Okay. So, thank you very much. I think it's time.